Okay, to conclude our chapter on complex numbers, we do some exercises. All these exercises are taken from exams for first-year students at German universities. Those were exams in mathematics for engineers and electrical engineers. I'm not doing all the exercises. The students of mine have an exercise sheet, but just some of them. That's why we start with number 1C. So you're supposed to draw the following sets in the complex plane. The set M is given by all complex numbers that satisfy this inequality, the modulus or absolute value of z minus 1 plus I, in parentheses, is less than or equal to 1. And the set N is given by all the complex numbers that satisfy this equation. The imaginary part of z is 2 times the real part of z minus 1. Now the first should be obvious if you ever saw one of these before, because this is simply a circle. No, better, it's the whole disk. If I would have an equal sign here, it would be a circle. And here less than or equal to means the whole disk with center 1 plus I. Okay, and since it didn't say justify your answers or anything, simply draw the following sets. You get full credits for actually drawing simply this disk here. Okay, that should be fine. It actually said draw sketches of the following sets. So if you didn't happen to have a compass with you in the exam, it was all right. So here the center is 1 plus I, and the radius of the disk clearly is 1, because this here is the distance between z, so any point capital Z, which corresponds to the complex number small z, which has distance less than or equal to 1, lies in this set. So this here is the whole disk, and it's very important to shade the whole disk. It's not just the boundary, the circle of radius 1, but the whole disk of radius 1. Now this looks a bit strange at first sight, but then if I write the numbers z in standard Cartesian form, x plus yi, with real numbers x and y, then this here simply becomes y equals 2x minus 1, and this obviously is a straight line with slope 2, and it intersects the imaginary axis at minus 1. So in the exercise sheet that my students have, we have a minus 3 here, but I didn't want to go down to minus 3, so I changed that to minus 1. So this has another advantage, namely the line passes through 1 plus I. I go 1 to the right and 2 in imaginary direction, and then this straight line here is the set N, and that's it. So that's a truly nice and easy exercise for a math exam at university level. So next exercise, number 2a. You're supposed to solve this equation. Z to the third power is minus 64 times I, the imaginary unit, and the solutions must be written in polar form and in Cartesian form. The first step to solve an equation like this is to transform the right-hand side into Cartesian form. So the length of this arrow here obviously is 64, and all we have to do is write minus I in polar form, which is because the angle of minus I is 270 degrees or 3 pi over 2. And now to obtain one solution, we simply draw the third root of the length, and we take this angle divided by 3. So we end up with that. I call this one particular solution W, in German Wurzel, root in English. So third root of 64 is 4, and here we have e to the pi over 2 times I, and this is nothing but I itself, so one solution is 4i. Of course, in this case, if you know that I to the third power is minus I and that the third root of 64 is 4, you could write down this directly as one solution. And now it's always the same trick with equations like this. You simply multiply this one solution with all the 3 roots of unity. So the third roots of unity, in German die dritten Einheitswurzeln, are zeta sub k. You simply take 2 pi divided by 3, this number here, and then you multiply it by 1, 2 or 3. And of course times I. These are the 3 third roots of unity, and if you multiply these with w, you end up with all the solutions of this equation. That's what we have here. All the solutions are z sub k equals w times zeta sub k. So here I write w again in polar form so that I can multiply easily with the first third root of unity. And this, doing a little bit of fractions, is 3 pi over 6 plus 4 pi over 6 is 7 pi over 6 times I. And now I have to transform this also in Cartesian form using Euler's identity. And please take a note, no calculators allowed at all in these exams. So you have to do this by hand. Okay, now 7 pi over 6 radians corresponds to 210 degrees. Pi is 180 and pi over 6 are 30 degrees. So we are here on the unit circle. So we see that the cosine is negative. The cosine of 30 degrees, that you should know by heart or use this tabular, is square root of 3 over 2. So we have a minus sign and then a square root of 3 divided by 2 plus, and the sine of 30 degrees is 1/2. We're also in the negative part, so we have minus 1/2 I, and multiplying by 4 gives us minus 2 square root 3 minus 2i. And this is another solution of our equation. Okay, the same with zeta sub 2, which is e to the 4 pi over 3 times I. Then adding these fractions, I end up with 4 times e to the 11 pi over 6 times I. Now 11 pi over 6 corresponds to 330 degrees. So by symmetry on this unit circle here, I see that the cosine is the positive value of this here, so square root 3 over 2, and the sine is minus 2. So I end up with this solution here. And the last one is the easiest, because zeta sub 3 is e to the 2 pi I, which is nothing but 1. So this is w itself. So we have 4i, and that's it. The 3 solutions of this equation in polar form and in Cartesian form. Okay, next exercise, number 3a. You were given 3 complex numbers and should draw them in the complex plane. I picked out this one. This is the hardest one. 1 minus I to the 7th power. And of course you do not want to use the binomial theorem to expand this bad boy, but the easiest way would be to write this here in polar form. 1 minus I. The length, of course, is the square root of 2. 1 squared plus 1 squared. There's a 1 in front of the I. So I have the square root of 2 as the modulus, or the absolute value of this number. So, and then this angle here is minus 45 degrees, or minus pi over 4. So we have this expression for the polar form. Normally we would like to have angles between 0 and 2 pi, but for this calculation here the minus also is okay, it's actually easier. Okay, now using the power rules, this here is square root 2 to the 7th power, and then I have to multiply this exponent here by 7, which gives me this, and this is the same as 2 pi minus 7 pi over 4. Or you wonder, like so. Okay, now there's a little trick. You could either use Euler's identity as before, and you would have to know that cosine of pi over 4 is the same as sine pi over 4, and they equal square root 2 over 2. And so you could multiply here, but a better trick is that you see as here, same as here, 1 plus I is square root 2 times this guy here. So I split up this power here. I draw out square root 2 to the 6th power divided by 2, and then here I'm left with 1 plus I. This here is 2 to the 3rd power, so 8. So this gives me 4 times 1 plus I, and this I can draw easily. This is this vector here, but longer. The length is 4 times square root 2. So I simply take this arrow here and multiply its length by 4. So another trick to do this without the polar form would be to write the 7th power as this guy squared to the 3rd power times this guy. Now 1 minus I squared gives you a nice expression that you can easily raise to the 3rd power, and then you simply have to multiply with 1 minus I. You should try this yourself and arrive at the same result. Okay, part B of this exercise was, again, this is original exam question at German universities. You should sketch this set here, given by 2 conditions. Now, the first condition, if you have solved this one here, should not be too hard. This here describes a disk of radius 2. But we take something away from the inner disk because it has to be larger than or equal to 1 at the same time, this distance here. You should write this in this form because only then you can see that the center of the disk lies at this complex number minus 3 plus I. Okay, here's a rough sketch of the set described by this first condition. Here the center is minus 3 plus I, minus 3 plus I. Now this here would be a disk of radius 2, so the whole thing. And this here takes away the inner disk of radius 1. So the whole set would be an annulus, in German Kreisring. But now we haven't considered the second condition. For this I write C plus 2i is x plus yi plus 2i. So this number here is, as always, x and y are real numbers. X plus y plus 2 times I. So the imaginary part of this guy here is y plus 2. So I end up with the condition y plus 2 must be less than or equal to 3, or simply the imaginary part of our number z must be less than or equal to 1, which is a half plane. So if I take the 2 conditions together, here the blue one would be the shaded region below this dotted line, including the line, because we have this equal sign here, and this here would be this annulus. So taking both conditions together, gives me this shaded region. Observe blue and yellow together give green. Isn't that nice? So, and very important, the boundary belongs to this set M here. If I would have a smaller sign here and here, I would have to dot the boundary. So this is very important, all right? So this here would be the set M. And if this here is the problem, sketch the set, you get full credits for simply sketching this set. But, of course, it is always better to show your reasoning, because if you make a mistake here and you do not write down this, there's no way that the corrector has any chance to see what your thoughts were, and you simply get 0 out of full credit points. Okay, next one, number 4a. You should write this complex number here in polar form. The exact formulation of the problem was find the modulus and find the argument or the angle of this number here. Okay, so of course we transform this into polar form, and then we take the fourth power and we see the angle and the modulus. So I call this number here W, and then the modulus of W is square root 3 squared plus 1 squared, which is the square root of 4, which is 2. Okay, and the argument of W is the arctangent of the imaginary part, so 1 divided by the real part, which you can see here. And this you have to know by heart, that this here is 30 degrees or pi over 6. Because if you have memorized the values of sine and cosine, then the tangent is nothing but the sine divided by the cosine. And this exactly corresponds to pi over 6, which you could also have guessed by looking at this arrow here. So, of course, then the absolute value of z is nothing but the absolute value of w to the 4th power, so 16. And the argument of z is 4 times the argument of w, because by raising the polar form to the 4th power, I take the angle times 4. So this is 4 pi over 6 or 2 pi over 3. So z would be that number in polar form, and that's it. And of course now, if it were asked, you could use Euler's formula. This here is 120 degrees to write this back into Cartesian form. So the exercise could also have been write this here in Cartesian form. I would always recommend that you take the detour with the polar form instead of using the binomial theorem. Okay, now number 4b. This looks unusual at first glance, but is not that hard. You are given a circle K, German Kreis, in the complex plane, and you should find a real number S such that this set in the complex plane is exactly this circle K here. We start by writing down the usual equation for a circle. K is described by the complex numbers that satisfy this condition. The distance to 2i, which is the complex number corresponding to the center of the circle. Here's the arrow 2i, or the endpoint of the arrow 2i. So the distance between z, any point on the circle, capital Z, to this complex number must be 1, because of course the radius of this circle here is 1. So this condition here becomes that. Now I take together y and minus 2, forming the new imaginary part of this expression here in the modulus. And now the absolute value or modulus is the square root of the real part squared plus the imaginary part squared. This must be equal to 1. And now I square this equation. Be aware that this is an equivalence because both sides are non-negative. So this here is important. You should write that down for yourself. So we have x squared plus y squared minus 4y plus 4 equals 1. So, and now we end up with this equation. This is the equation for this circle here in Cartesian real form with x and y. But now this here is nothing but the modulus of c squared, which is nothing but c times the complex conjugate of z. Here we already have y. Y was nothing but the imaginary part of z. So the number s we are looking for is minus 3. So the answer to this problem is s equals minus 3. Okay, this is enough for one video. The rest of the exercises is presented in video number 2. See you then. Bye bye.